Yep, it's going to be this Tuesday.
This Tuesday. Okay. So, what kind of material? I got this one paper from you. This one here?
Yep, that was the one we were looking at last time. There's a few other pages in there, but I've done the majority of it already. I just had a few questions for it, and
okay.
Yeah.
Do you have any questions on this one? Number 5.
Yeah. Actually, I do. Can we go over how to do that one?
Uh-huh. Notice, first of all, that nothing happens very good if I just distribute it. I get this. And even though that'll turn into square root of 45, I still can't do much with it.
Mm-hmm.
Okay. But notice what happens if I break this up into root 5 times root 3 . And now if I distribute it, up here I get 4 root 5 root 3 minus, and I've got this 3 there, but I got a root 3 and a root 3 that'll turn into another 3. So it'll be 9 root 5.
All right.
Hold on a second. Did I do that right? Let's see. I multiplied that by that to get that term. And now I'm multiplying that by that. So I get 3 times 3, which is 9 root 5. Yeah. Now, I can simplify it a little bit. I can take a root 5 out, and leaving 4 root 3 minus 9. I don't know that that's necessarily simplified. I feel like I made a mistake here. I feel like we should almost be... The first time I looked at this, I thought we got down to a position where I had root 5s together, and then I could simplify them. And I guess this is that. Do you have answers on these?
Yeah, I do. I'm looking at it right now.
Yeah, what their answer says. I'm a little curious. You could have various answers.
The answer is 4 root 15 minus 9 root 5.
Which is this answer up there. In other words, if I put this back together again, it becomes 4 root 15 minus 9 root 5. I guess, you know, in thinking upon it, the easiest way to do this is really just to do it straight away. In other words, if I go ahead and distribute it, I get the 4 root 15 minus, and then I could separate it at that point into this, and then I'll end up getting my 9 that way. That's probably the easiest way to look at that problem. Not to separate it first, but separate it last.
All right.
All right. Got anything else on this page? You're good with 6?
Yeah, I'm good with number 6.
Okay. How about and 7? Looks like you've done that properly. Yeah. So the other pages, whoops. Have you sent them to me, or?
I was just gonna verbalize them because they're all pretty.
That's fine.
Problems, I guess.
That's fine.
So
go ahead.
The next one, it's write each expression in exponential form, and it's root 5p, and all of that is to the 5th power.
Root 5p?
Yep. To the 5th.
Like this?
Yeah.
Okay. When you have a mixture of radical signs and exponents, I like to put everything in exponents. Okay? So I'm going to take this 5p and remove the radical sign and put parentheses around it, and those are definitely needed, and take it to the 1/2 power. With me?
Uh-huh.
Now I'm going to use the rules of exponents. So this gets multiplied together and gets applied to each thing. So I end up with 5 to the 5/2 power times p to the 5/2 power. Now, if I really have to put it back, some teachers, if they give it to you with radical signs, they want radical signs back. Each of those would be to the 5th.
Okay.
That's what we started. No, that's not quite what we started with. But we started with this. All right. What else?
All right. Yeah. They gave it in just the complete exponential form. But all right.
Oh, hold on. What was that?
For that problem, they just gave the answer in the like fully exponential form. So 5p.
Okay. I got you. I got you. Uh-huh. Okay. That's right. I have remembered now that they had asked that. In fact, when you started the problem, I thought it was a log problem. Because usually when you're putting something in exponential format, it's a log expression.
Mm-hmm.
Okay, what else you got?
This next one's a log expression.
Okay.
It's condense each expression to a single logarithm.
Okay.
And the problem is 2 log 7.
2 log base 7?
Nope, 2 log base 10.
Okay, so 2 log, yeah, I don't know how you, I guess you can just say that, 2 log 7. Okay.
And then it's plus log base 10 of 11. And then just the log 11 is over 3.
Like that?
Yep.
Okay. There's 3 log rules. Or, do you know them? What's the log of A times B equal to?
Is it just log of A times or plus log of B?
Yes. In other words, you don't do, if the argument is multiplying, you're not going to multiply, you're going to add. If the argument we are dividing, then we are not going to divide, we're going to subtract.
Mm-hmm.
Logs are exponents, so they have the same rules that exponents do. And then this one probably is the most important one. You use this third one a lot in calculus. Okay? So those 3 rules. Those handle all of our expansion and division problems. Or, excuse me, our expansion and condensing. Now, this is a condensing one. And what I usually suggest to students is they just go in the reverse order. In other words, if I was expanding it, I would use rule 1 first or 2 first, and then 3 at the end. But if I'm condensing it, I want to get rid of these coefficients. So I'm writing this as log of 7 squared plus what?
Plus log 11 over 3.
No.
Log 11 minus log 3.
No. This is where that 1/3 belongs.
Oh. Okay.
Right? In other words, this is the same as that. It's just when you divide by 3, that's the same as multiplying by 1/3.
All right.
Okay, and now I can put that 1/3 as the exponent. So it goes there. So that's the first step of condensing. I've gotten rid of the coefficients in front of the log. And now turn that into a single log expression.
Okay. Do you just multiply together and add exponents? Or
Okay, here's what we're doing. Here's what we're starting with on the right. That's what this is here. So to turn it into a single log expression, you're going to take the log and multiply that times that.
Okay.
So it's 7 squared times the cube root of 11. And of course you can turn that into a 49 pretty easily, whereas we're going to leave the cube root 11 that way because that's an irrational number. So your answer should be this.
All right.
Okay, what else?
The next one is just solve the equation of log base 6 of 4x equals log base 6 of 3x plus 10.
What's the next step?
Let's see here. Since they both have the same log base, could you just solve it algebraically?
You would equate the arguments, is what that's called. Yeah, a lot of people like to think, can I just divide both sides by log base 6? And in a way you can, although that's not at all what you're doing. In other words, when I write log base 6 of 4x, that is not log base 6 times 4x. That is more like this means a function of x. It doesn't mean f times x. Okay? So what I'm really doing here is if the log base 6 of this argument equals the log base 6 of this argument, then this argument has to equal that argument. So that's what I'm going to do. And then it's easy to solve. X equals 10.
Okay.
Okay?
All right.
Hold on 1 second. Clyde, come on. Clyde. Clyde, come on. Come into my office. Clyde. Come on. Sorry about that.
Oh, you're fine.
Okay, what else?
The next one is just evaluate the expression, and it's log base 3 of 27.
Get a lot of problems like this, okay? And the easiest thing to me is to set it equal to what you want. In other words, let's introduce a variable and say we're going to let this thing equal x, and now I can solve it because you know how to switch from exponential to log and log to exponential, I hope. Do you know how to express this exponentially?
Yeah.
What is it?
Isn't it just, hold on, 3 to the x power equals 27?
Yeah. The way I remember it is it's the number on the far left raised to the power on the far right equals the argument. And always remember, logs are exponents. If you remember only one thing about logs, it's that they are exponents. So when I'm looking at this expression, this top expression here, I know that x has to be the exponent. I know that for sure, very first thing. Now it's the question is 3 to the x equal 27, or is 27 to the x equal 3? Well, this thing's always the base, and that's the base. So being able to go back and forth between logs and exponentials is super important and fast. You want to get really good at this. It's not that hard. In other words, to express that exponentially. Now what's x? See, now we can solve for x real easily.
Yep.
What is it?
Well, 3 raised to the third.
Uh-huh. Okay, what else?
Oh. All right.
All of those kind of expressions, when they want you to solve it by converting it to exponential, they're always going to be low whole numbers. In other words, it's not going to be, x isn't going to be 3.12 there.
Yeah.
Because if it was, then we wouldn't solve it by converting to exponential. We would solve it by putting a log answer. So you always know that you're looking at low whole numbers for those expressions.
That's really nice, actually.
Yeah, it is. It means you can do them without a calculator, basically. In other words, let me give you one. Evaluate that.
So it's 4 to the power of x equals 64.
Is x equal to?
X, let's see here. Is it 4?
Do a couple of experiments. In other words, test out your answer. Is 4 times 4 times 4 times 4 64?
Oh no, that's way too high. Would it be 4 cubed?
Exactly. Like I said, usually low whole numbers. And that's because they expect you to know your powers, your cube numbers up to, I don't know, 125. And they expect you to know your square numbers up to probably 7. But they don't expect you to know your 4s. In other words, they may expect you to know 4 cubed, but they don't expect you to know 4 to the 4th.
Yeah.
All right?
Okay. All right. So this next one is evaluate the infinite geometric series, and it's the Greek letter thing. I'm not sure what it's called, but it's like the, I don't know, the reverse
Sigma?
3.
That?
Yeah, that.
Okay, that's sigma, which means sum. Okay.
And then the bottom is m equals 1. And then it's to infinity. And then the equation on the right is 32 times negative 1/2 to the m minus 1.
Like that?
Yep.
The n minus 1 is the exponent?
Mm-hmm.
Okay. If you're evaluating well, let's talk about geometric series. The geometric series is defined as, do you know the general formula for the nth term?
Is it the a sub 1 over 1 minus r?
It's a sub 1 times the common ratio to the n minus 1. Okay?
All right.
In other words, if we write out a few of those first two terms, we don't really need to if you have the other formula that I'm going to talk about memorized. But if we write out the first few terms, when n is 1, that's 0. So that becomes 1. So that's 32 is the first term. So, and we're always adding these. That's what the sigma sign means. And the second term is 32 times minus 1/2 to the 1 power. That's minus 16. Okay. And then the third term is when n equals 3, which makes that an even number, makes it 1/4, and we have plus 8. So this is going to be an alternating sequence, okay? And clearly what we're doing is multiplying each term by minus 1/2.
Okay.
Okay? So the next term is going to be minus 4. The next term is going to be plus 2. The next term is going to be minus 1, plus 1/2, and so forth and so on. So we have an alternating series that is declining. And we have a formula for the sum of an infinite series. Do you know the formula?
Is it S sub n equals n times a sub 1 plus a sub n over 2?
That is for an arithmetic sequence. For a geometric sequence, hold it, that's not A, that's R. Hold on a second, let me just double check. Make sure I'm giving it to you right. I'm 95% sure I am. Sequences in series 666. I get these just seldom enough that I don't always have them memorized. Yeah, it's a sub 1 over 1 minus r. Just 1 minus r. Not even to the n. So I did have it wrong. Hold on a second. Sum, yeah, if it's a, well, hold on. Am I wrong, folks? But I think no, it's a sub 1 over 1 minus r. That is the sum of an infinite geometric series. Now, there is, r is this. Whatever's in the parentheses, that's r. Okay? So this is going to be 32, the first term. I guess that's a sub 1 over 1 minus r, all over 1 minus a minus 1/2. So this is 32 over 3/2, or 64/3.
All right.
And notice that that kind of makes sense. In other words, we're starting out with a 32, but then we're subtracting 16, but then we're adding 8, then we're subtracting 4. But really, that's the formula. I didn't really need this formula. I just wanted to make sure you knew it, since we were talking about geometric sequences. But if you're adding up an infinite series, and that's what we're doing here. In other words, this keeps going forever. But if it's an infinite series, you can use, and if it's a geometric series, you can use that formula. Now, notice what happens if this term here is greater than 1. In other words, if It's only a convergent series if the absolute value of what is in the parentheses is less than 1. If I go up there and stick a 2, then that series goes off to infinity. It only converges if r is less than 1.
All right.
That's the only time you can use that, is if we're dealing with something in the parentheses that's less than 1. If I make that a 1, notice what happens is the term becomes 32 plus minus 32 plus 32 minus 32 plus 32. That is a non-convergent series. In infinite series, there's only really the very first thing that matters is whether they are convergent or divergent. If they are divergent, they are not worth talking about. There is nothing to discuss. But if they are convergent, like this one, then it's nice to know what the sum of all the terms would be, and it's that number right there.
All right.
Okay, what else?
All right. So, the next one is evaluate the arithmetic series.
Okay.
So it's the sigma with k equals 1 going up to 11. The equation is 3k minus 4.
Okay. We could certainly do this the hard way, which is to write out the first 11 terms and add them all up. Okay? But we don't need to do that. We have a rule for arithmetic sequences also. And here is that one that you read to me. The nth term, not the nth term, the sum of the first n terms is equal to the first term times 1 minus, oops, got the wrong one here. Just a second, I was on geometric. The arithmetic is n, the number of terms, times a sub 1 plus a sub n, the last term, all over 2. Okay.
All right.
And, well, it's not quite all right because we don't know what a sub n is. In other words, it's easy enough to figure out the first term. What's the first term?
1.
It's negative 1. In other words, the first term k is 1. But if I plug it in, my first term of that series is negative 1. You see why?
Oh, yeah.
Okay.
Minus 4.
What's the last term? In other words, I don't need all the middle terms, as all I need is the last term, the nth term, or the 11th term.
Okay.
What is
So
the
then,
11th term?
would it just be 33 minus 4, so 29?
Uh-huh. Now we have everything we need to figure out the sum of the first 11 terms. Plug it in. Tell me what I should write.
All right, so then S of 11 equals 11 times negative 1 plus 29 over 2. So 28 over 2 is 14 times 11 is 154.
Uh-huh. And clearly that's the faster way, is to figure out the first term and the last term based on this. And, you know, they can make these things tough. They could have said go to 111. And then it'd be almost impossible to do it manually. You would have to use the formula.
Oh, yeah. Okay.
So let me give you a classic problem that one of the most famous mathematicians got when he was an 8-year-old. in math class. What's the sum of the numbers from 1 to 100?
The sum of the numbers from 1 to 100?
Uh-huh.
So that'd be S of 100 equals 100 times 1 plus 100 over 2.
Yep. That's it.
So then 101 divided by 2 is 50 and a half times 100.
I believe that's the answer.
Yep, 5,050.
Uh-huh. Now, he did it a little different way when he was 8 years old. He recognized that the first and last number add to 101, and the second and second to last number add to 101, and so forth and so on, until you get down to 49 and 51 add to 101. So he's got 50 pairs, or rather 49 pairs, that add to 101 plus that 50th number, the one in the middle. Yeah, I did something wrong there. Let's see, it's 4952, and then the last pair is 50, 51. So he has 50 pairs that all add to 101, so he multiplied 50 times 101. And that's the way he did it when he was 8 years old.
That's pretty good for an 8-year-old.
Yes, it is. Well, he became one of the great, that was Gauss, became one of the great mathematicians, yeah.
All right.
He was a child prodigy for sure. What else do you got?
All right, so this next one is a graphing one. So it's using radians, find the amplitude and period of each function in graph.
So, okay, go ahead. So you're going to read a function, and then we're going to find all that stuff and graph it?
Yep.
Okay, go ahead.
So the equation is y equals 2 cosine theta over 3. Yep, just like that.
Let me write the general format of a sinusoid wave. And tell me if this is the one your school uses. Yes? No? That's a D?
I don't think so, but...
Okay, so either you use different letters or you haven't gotten to phase shifts and vertical shifts yet.
We have, but usually what she does is she just has us, like, start out with the parent function and then make the shifts from there. But
Okay, is your B inside or outside the parentheses typically?
outside.
Just like this.
Well, it might be the same formula, she just never showed it like that to us.
An example of that, a full one would be something like that. Okay? That's
Yeah,
amplitude.
Yeah, she's used that one with us before.
Okay, that's B. And B relates to the period in the following way. B equals 2 pi over the period, which makes the period 2 pi over B. Okay, so that's what the meaning of B is. The pi over 4 is C, and it is a horizontal shift to the right by pi over 4. They call it a phase shift. But don't kid yourself, it's exactly the same as a horizontal shift if we were dealing with an algebraic equation. And then finally, the D is the vertical shift, exactly the same as a vertical shift. In fact, all of these are exactly the same. A is a vertical stretch or shrink factor. B is a horizontal stretch or shrink factor. C is a horizontal shift, and D is a vertical shift. And then if I want to do reflections, I stick a negative sign there. That's a vertical reflection. If I want to do horizontal reflection, I put a negative sign inside the parentheses. So that's how it works. Okay? So what did they ask? They wanted the amplitude, right?
Yeah, the amplitude and the period.
Okay, the amplitude's 2. What's B in our problem here?
B in this problem is 1.
It's 1/3. Again, don't get thrown off by that. That is the same as 1/3 theta. The coefficient in front of theta is 1/3. Okay?
Okay.
So, what's the period? In other words, once you figure out what B is, then you need to figure out the period in order to graph it.
So 2 pi over 1/3.
Which is
6 pi.
okay. Now we got enough to graph it.
All
In
right.
other words, there's no phase shift and there's no vertical shift. So
Nope.
it's pretty easy to graph. First of all, let's graph the regular cosine that's unadulterated. Or by that I mean not no amplitude. In other words, it goes up to 1, down to -1, and goes out to 2 pi.
Yeah, the original.
That's y equal cosine of theta. Well, in our case, we have 6 pi. So rather than draw it off my screen, I'm just going to label that thing 6 pi. Okay? And this is going to go up to, instead of 1, it'll go up to 2, and it'll go down to 2. Okay? Now, here's the most important part about graphing it. Once you've determined its starting spot and its ending spot for one period, what you have to do is quarter that up. Have you heard that expression?
No.
Find the quarter points. The quarter points are the key points with all sine and cosine functions. They're huge. In other words, that quarter point, which is the halfway point between my start and my end, which is 3 pi, that comes when the cosine hits its lowest value, -2. And then the other quarter points, that's the halfway point between those 2 points, which is add the 2 points, divide by 2. So that's 3 pi over 2. Over here, I'm going to add 3 pi to 6 pi and divide by 2. So that's 9 pi over 2. And those quarter points are key. That's where the cosine curve comes back down and goes through the x-axis, or goes through its horizontal line of symmetry. And so the first quarter point is huge. The start at 0 is huge, because cosine starts at its highest point. And you can see that if I wanted to graph this thing, my quarter points are absolutely necessary. If I want to graph it, I'm not starting with the graph, I'm starting with these quarter points. And there's 5 of them, because there's the beginning one, there's the ending one, and there's the 3 in the middle. Okay? And I'm starting there, meaning I know I'm going to put an X there, 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 and I'm going to contact my starting spot. And now all I have to do is draw a cosine curve that goes through those X's.
Cool.
I get a much better looking cosine curve. But this process of quartering up the x-axis is huge. Every time you graph one of the formulas they give you, you pretty much have to do that. Unless it's just 2 pi is the period, and then it splits up pretty easily. You have pi, pi over 2, 3 pi over 2. But usually the period isn't going to be 2 pi, because they're going to give you a b in all of these, I suspect. You have another one?
Yeah. y equals 4 sine 2 theta.
What's A?
No, 2 theta, sorry.
Excuse me. You said that. I just didn't hear it. So what's A?
So A in this case is 4.
What's B?
B is 2.
What's the period?
Is it just pi?
Huh? Notice, just like an algebraic, that scrunches it up, right?
Mm-hmm.
In other words, when you have a transformation of an algebraic or polynomial expression, if you have a number greater than 1 in front of the x, it compresses it, which is exactly what this is going to be. So I'm going to start at 0. That's where sine starts. And I'm going to go out to pi. That's where I'm going to end, which means I kind of come back to 0 there. Now I'm going to quarter it up. That's pi over 2. That's pi over 4. That's 3 pi over 2. Excuse me, it's not 3 pi over 2. It's pi over 2 plus pi, so it's 3 pi over 4.
Mm-hmm.
Sometimes it's actually easier to write these without simplifying them. You'll notice that I could have written this one as 2 pi over 4 and this one as 4 pi over 4. Now I got 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So I know I've quartered it up perfectly.
Yep.
Now, I know sine starts at 0. Where's it go up to and where's it go down to?
It goes up to 4 and down to -4.
And I know that at the first quarter point, sine hits its high mark, comes back down through the x-axis at the second, goes down, hits its low mark at the third, comes back to there. So now I just got to draw a sine curve through that.
Awesome. All right.
And they have not introduced you to phase shifts and vertical shifts yet, or just haven't done much of it?
They have. It's just in the
Okay.
study guide.
When you do phase shifts, this is the most important part, quartering it up, knowing where you start and where you end. For example, let me just give you a quick one. Y equals sine of x minus pi over 4. Okay? In other words, the only thing I'm going to do here is do a phase shift.
All right.
What is, in this case, the period is 2 pi, right?
Right.
Where's my starting spot?
Your starting spot? Normally it would be 0, but in this case it's 0, no. Yeah. 0 negative pi fourths.
Well, it's actually pi over 4 comma 0.
Okay.
You see why that's my starting spot? That's a horizontal shift to the right by pi over 4.
All right.
You with me? So
Yeah.
that's where I'm going to start. Where am I going to end? That's the next thing to figure out.
So if you're starting at pi over 4 and you have a period of 2 pi, 2 pi over, no, 2 pi over 4, so I'm going to say 9 pi fourths.
There you go. 9 pi over 4 is 2 pi plus pi over 4. Now we got to quarter that up. In other words, let's find the midpoint. And the way you do it is just add the two numbers and divide by 2.
So 10 10 pi over 4 divided by 2.
It's 10 pi over 8. Simplify that.
Right. 10 pi over 8, so 5 pi 4.
5 pi over 4. Now quarter this up. What's that? And you can kind of see a pattern here. This is 1 pi over 4, that's 5 pi over 4, that's 9 pi over 4. So you don't always have to do the math. What's the midpoint between pi over 4 and 5 pi over 4?
3 pi over 4.
What's the midpoint between 5 pi over 4 and 9 pi over 4?
7 pi over 4?
Yeah, in other words, sometimes they're just so easy you don't have to go through the math. You just have to, it's easy to find those 4 quarter points. Okay, now I know that at my first quarter point it hits its peak, comes back down to the second quarter point, hits its negative at the third quarter point, and now I'm going to draw it. That's how you do it. Whenever you're dealing with a phase shift, that's what you should do, is find out where your starting point is and where your ending point is. And then quarter it up and then draw the rest of it. And I could add most anything to this. I could add a 2 there. I could change the period by adding a 3 there. I could change the vertical shift, but none of it effectively matters. You're still going to go through that process of quartering it up between your beginning and your ending point. Okay. And always remember that that's a shift to the right. Just like x minus 2 squared would be a parabola shifted to the right by 2 units.
Yeah, the opposite shift.
Well, yeah, it's the opposite of that. In other words, I don't really call it that. To me, the formula is x minus c. Just like here, it's x minus h. And h is a positive number, too. And here, c is a positive number, pi over 4. And positive numbers go to the right. So, in a way, you can look at it as the opposite direction. But it's nice to know that the regular format of it is x minus c. Although there are some school systems that use x plus c, believe it or not. And then the phase shift is negative c over b. There's actually a surprising number of general formats for that sinusoid equation. What else you got?
All right. So the next problem is, let's see here. Find a coterminal angle between 0 degrees and 360 degrees. And it's for negative 105 degrees.
The way you find coterminal angles is you just add 360.
Okay.
So in other words, any angle can have 360 added to it, and all the trig functions are the same. So that's the same as a 255 degree angle. In other words, the sine of negative 105 degrees is going to be exactly the same as the sine of 255. Now, if I want another coterminal angle, I could actually add another 360. That would be 715. That's also, all the trig functions are the same as that.
All right.
It wanted just one, and it wanted it to be between 0 and 360, so that is the answer to your question. But the fact is, coterminal angles are any multiple of 360, plus or minus. In other words, I could take this minus 105 and subtract 720, and I would still have a coterminal angle.
Awesome. Okay.
What else?
So the next one is find the exact value of each trigonometric function.
Okay.
And it's secant of theta with it being, they have like a graph, and it's negative 17x over 3.
Like that?
Pretty sure, yeah.
Secant of theta equals that?
Yeah.
And they want you to solve for x, right?
Mm-hmm.
I don't think so. This has a theta in it and an x, so I can't. I got two variables. That's a variable, that's a variable. You've only given me one equation.
So
I can't solve for it. Here's what I suspect the question is. If the secant of theta is minus 17 over 3, give me another trig function of theta. Tell me what the sine of theta is. Is that possible that that's what they're doing here?
I don't know.
This is kind of the classic trig question, where they give you one trig function, and they give you its ratio, and then they ask you about other trig functions. Okay? The one thing I can do with that information is draw a triangle and label theta. And now they're telling me that the secant of theta, which is the hypotenuse over the adjacent, is 17/3. It's negative, but all that tells me is that which quadrant it might be in. That means it's either in the second or the third quadrant. They haven't told us that, and they need to tell us that. But the fact is that I drew a right triangle, and so I know what that is. That's 17 squared minus 3 squared. So now I have a triangle that has all three sides dimensioned, and without ever figuring out what theta was, I can figure out the sine of theta, the cosine of theta, the tangent of theta, all of them. But the one additional piece of information they need is, let's put it in the correct quadrant. It's in the second quadrant. I made that up because it could be in the second or the third. Secant is negative in both of those quadrants. So I'm saying it's in the second. Okay? Well, now if it's in the second, then the sine of theta is positive. So the sine of theta would be opposite over hypotenuse. That's what the sine of theta is. And I could do any trig function based on this picture over here and based on which quadrant it's in.
All right.
I'm still a little unclear as to what that question was asking. I might have gone off on a different path, although the path I went off is probably, if you were going to take a trig test and they were only going to give you one question, this might be it, the one I just went through.
All right.
Not with these numbers, but the question, they would give you a trig function's value, and they would tell you which quadrant it was in, or they would also say tangent of theta is greater than 0. Well, that tells you what quadrant it's in. What quadrant is it in? If secant is negative and tangent is positive, there's only one quadrant where that happens.
I'd put it in the third quadrant, right?
So that would be the third. And now I draw the same picture, I label it the same. The only thing is the sign is now going to be negative because it's in the third quadrant. So it'll be that same answer, only it'll be negative. Okay? So you always need two pieces of information to be able to figure out what quadrant it's in, unless they tell you.
Okay.
Okay.
Cool.
What else you got? We got a few minutes left.
Yeah. All right. So the next one is find the measure of the angle indicated and round to the nearest tenth. So they give you a right triangle where the hypotenuse is 6 and the leg lengths are 5 and 4. And then the angle that they give you, theta, is across from 5.
What angle is that?
In this case, it'd be between 6 and 4 for you in the lower right-hand corner of the triangle.
What's the angle measurement?
It's just theta. You have to find the measure of it.
Ah, okay. This, incidentally, is not a right triangle. This is just a triangle.
Oh.
Okay.
I solved for the
If
6.
it were a right triangle, we could solve for theta relatively easy. We could say the inverse tan of theta equals 5 over 4.
Okay. I solved for 6, so that might be where the issue in that one is.
Might be a 3, 4, 5 triangle, if it's a right triangle. And it would have to be. We don't have enough information. No, actually we do. Have you had the law of sines and the law of cosines?
Yeah.
Okay, so it's not a right triangle. We can still solve it. The law of cosines is used whenever you have side, side, side.
Yeah, so the way that this problem's set up, though, is that they don't give you this 6. I solved for that, and I thought that I had it written down. They give you a right triangle where the two legs are lengths 5 and 4.
Okay, cool. So what's the hypotenuse?
The hypotenuse in this case, 4 squared plus 5 squared, right?
Right. So it's 25 plus 16, so the hypotenuse is root 41. Okay.
Okay.
Now, if you wanted to solve for theta, because it's a right triangle, you can just use an inverse trig function, and you can use any of the 6. Pick one. By that I mean I could say the sine of theta equals 5 over root 41, which would make theta the inverse sine of 5 over root 41. And there's no real need to rationalize that, because notice we're coming up with theta. I don't care if the argument's not rationalized. It's the same numbers if I were to rationalize. Now, do you know how to get that angle out of your calculator?
Yeah, you just plug it in, right? You'd have to take the root out of the denominator.
You have an Inspire or TI-84 or what do you have?
I've got the TI-84 Plus.
Okay. So you know where the inverse sine key. It's the blue one.
Yep.
Above the sine key. And then just put in the argument. And it'll give you theta. Now, do you know whether you're in radians or degrees?
Right now I'm in degrees.
Okay. You know how to change that easily? That's
not
the only thing on the TI-84 that's better than the Inspire, is switching back and forth between radians and degrees. It's really easy on the TI-84.
All right.
Okay, so what's theta equal to?
They give 0.896 for the inverse sine of 5 over root 41.
That looks like radians.
All right. Yeah. So in degrees, it's it gave me an error. Oh, I see. Hold on. Okay, that gave me 51.3.
And that makes a lot of sense. That would be, first of all, it has to be less than 90. And it's a reasonable size triangle, so it's not going to be like a 89-degree angle. In other words, it's in the ballpark, which means you did it right. Notice that when you were accidentally in radians, I spotted it right away, because that's not a typical angle. In other words, if we want an angle in degrees, that doesn't look like it. So I'm pretty sure you were in radians, not degrees.
Yeah.
If you are ever in doubt, even though on that calculator, I believe it's the Inspire that shows you at the top. If you're ever in doubt, just do the sine of 30. If you get 1/2, you're in degrees. If you get anything else, you're in radians.
Okay.
Okay? And that's a quick little test that you can do real quickly. And that will tell you whether you're in degrees or radians and whether you need to switch it or not.
Okay.
Okay. Morgan,
Awesome.
that sounds good. I hope you're in shape for your test. You have any
Oh yeah.
last questions or understandings or anything that you want?
I'm actually doing pretty good. That was the entirety of the packet that I had left, so
Good.
thank you.
You're welcome. And you have a nice sister, a nice summer along with your sister. uh, and I will maybe work with you next year.
I hope so.
Okay. Have
All
a
right.
good summer.
Thank you. You too.
Bye-bye.